to Intelligence Gateway.
Module 3, Memory Management. Memory management is the process of controlling and coordinating computer memory, which is a crucial aspect of computer systems. Memory management is responsible for allocating memory resources, tracking which parts of memory are being used, and freeing memory resources when they are no longer needed. In computer systems, memory is typically divided into two main categories: primary memory and secondary memory. Primary memory, also known as RAM, random access memory, is the computer's temporary storage space, where programs and data are loaded for quick access by the CPU, central processing unit. Secondary memory, such as hard disk drives or solid-state drives, is used for long-term storage. In order to manage memory effectively, operating systems use several techniques, including virtual memory, paging, and segmentation. Virtual memory is a technique used to allow a computer to use more memory than it physically has available, by temporarily transferring data from RAM to secondary storage. Paging is a technique that allows the operating system to move data between RAM and secondary storage in fixed-size blocks, known as pages. Segmentation is a technique that allows the operating system to divide memory into logical segments, which can be allocated and deallocated independently. Effective memory management is essential for ensuring that computer systems perform efficiently and without errors. Poor memory management can result in system crashes, slow performance, and other issues that can adversely affect a computer's usability and reliability. Virtual memory. Virtual memory is a memory management technique that allows a computer to use more memory than it physically has available. It is a layer of abstraction between the program and the physical memory, where the operating system maps the virtual memory addresses used by the program to the physical memory addresses. This technique makes it possible for programs to access more memory than is physically available on the system. The virtual memory technique works by temporarily transferring data from RAM to secondary storage, such as a hard disk drive or solid-state drive. When a program requests data that is not currently in RAM, the operating system retrieves the required data from secondary storage and places it in RAM. This process is known as paging, and it allows the computer to store and access large amounts of data even if the physical memory is limited. The virtual memory technique also helps to improve system stability by protecting programs from each other and preventing them from accessing each other's memory. Each program is allocated its own virtual memory address space, which is isolated from the memory address spaces of other programs. This prevents programs from interfering with each other or accessing each other's memory, which can cause system crashes and other issues. Overall, virtual memory is an important memory management technique that allows computers to operate efficiently and handle large amounts of data. Paging and segmentation. Paging and segmentation are two memory management techniques used by operating systems to manage memory effectively. Paging is a memory management technique that involves dividing memory into fixed-size blocks, called pages. The operating system uses a page table to map the virtual memory addresses used by a program to the physical memory addresses where the pages are stored. When a program requests data that is not currently in RAM, the operating system retrieves the required page from secondary storage and places it in RAM. Paging can also be used to swap out pages of memory that are not currently in use, freeing up RAM for other programs. Segmentation is a memory management technique that involves dividing memory into logical segments. Each segment can have its own access permissions, allowing the operating system to control access to different parts of memory. Segments can be allocated and deallocated independently, making memory allocation more flexible. Segmentation can also help to reduce memory fragmentation, which occurs when there are small gaps of unused memory scattered throughout the system. Paging and segmentation are both used to manage memory effectively, but they have different strengths and weaknesses. Paging is generally more efficient for managing large amounts of memory, while segmentation is more flexible and can help to reduce memory fragmentation. Some operating systems use a combination of paging and segmentation to balance the advantages of both techniques. Overall, both paging and segmentation are essential memory management techniques that help operating systems to manage memory effectively and ensure that programs have access to the memory they need to operate correctly. Module 4, Input-Output. Input-Output, I/O, refers to the process of transferring data between a computer system and its external environment. This external environment can include devices such as keyboards, mice, printers, and storage devices. I/O operations can be classified as either input operations or output operations. Input operations involve receiving data from external devices and storing it in the computer's memory, while output operations involve sending data from the computer's memory to external devices. Input-output techniques. Input-output, I/O, techniques refer to the methods used to transfer data between a computer system and its external environment, such as devices or networks. Here are some common I/O. 1. Programmed I/O. In programmed I/O, the CPU interacts directly with the I/O device. The CPU must wait for the I/O operation to complete before proceeding with other tasks. 2. Interrupt-driven I/O. In interrupt-driven I/O, the I/O device signals the CPU when an operation is complete, allowing the CPU to perform other tasks while waiting for I/O operations to complete. 3. Direct Memory Access, DMA. In DMA, a DMA controller is used to transfer data between the I/O device and memory, bypassing the CPU. 4. Buffering. Buffering involves temporarily storing data in a buffer before it is transferred to the I/O device or the CPU. 5. Caching. Caching involves storing frequently accessed data in a cache to reduce the time required to access the data. For example, real-time systems may require fast I/O operations, while systems with large amounts of data may benefit from caching and buffering techniques.
Thanks for watching. For more information, like, comment, and subscribe our channel.